Thank you. Well, thanks, Dan and Ernesto and Lillian for a really good introduction to why we might want to consider doing weighted ensemble sampling. And so now I'm going to tell you about the software that we've been using to actually do this. Which is called WESTPA. So I'm currently at Drake University in Des Moines, which is a primarily undergraduate institution. I am using this code in my research group to simulate kind of similar questions, conformational changes in proteins, binding and unbinding rates. But I'm going to focus mostly on the design of this software, the kinds of things that you can do with WESTPA. You've heard concrete examples of this, but I'm going to go over in a little more detail of what that looks like and hopefully give you some ideas, get you thinking about what could the software do for you if you choose to use it. I really appreciate that Dan took the time to point out that there are many rare event methods out there. This is one of them. This is one software package for doing it. And so, of course, if we're proud of what we've done here with weighted ensemble, the method, and with WESTPA, the software. But I don't want you to think that this is the only thing that you can possibly do. So I'm going to show you some cool things that you can do with this if it applies to the systems that you're studying. The utility is broad. I think that if you want to do some rare event sampling, weighted ensemble is a good way to go. This software is a good way to set it up. And hopefully you'll leave a little more convinced of that than before you came. So I want to start by saying, why did we develop this software in the first place? So in 2009, I had just joined Lillian's group, and she was talking about wanting to do some of these protein binding and protein conformational change studies with the weighted ensemble method that Dan had recently kind of unearthed from the bowels of Biophysical Journal, where they had lain dormant for about 10 years. And so I sat down and thought, okay, if we want to do this on the biomolecular scale, what would weighted ensemble software need to look like? And part of this stems from the fact that although Dan had already developed code in his research group to do this, as a new grad student, the way I wanted to figure out how does weighted ensemble work was to sit down and implement the algorithm. It's one of these great algorithms where you can describe in one paper, one page of one paper really, the essence of the method. And so that was just tantalizing to me of, how can we, if you can describe this in one page, will this be feasible for a biomolecular system? Well, maybe I'll just sit down and write this. And WESTPA is kind of the third or fourth generation that started with that. But the kinds of things that we were concerned with is that, first of all, we need to be able to use this with multiple dynamics engines. We had already been talking about doing this, using these softwares using these simulations for all-atom explicit solvent models, for all-atom implicit solvent models, and for Brownian dynamics simulation, coarse-grained simulations of proteins. And so whatever we designed to do this had better reflect that kind of flexibility, that we were already looking forward to using this software with different dynamics engines under the hood. We needed the software to be flexible in simulation parameters. So one of the reasons that I think that we started with talks about what can you do with weighted ensemble, what are some of the concerns in using weighted ensemble simulations, that this was an evolving method. It still is now, and it certainly was then when the software was developed. And so a prime focus was making sure that we can make this software work for us, rather than, sometimes the converse is, okay, what is the software package that I'm using capable of? What will that let me do in my research? We wanted to be able to grow with this software. Another consideration was that we wanted to be able to store data efficiently. So Dan mentioned that these simulations can take gigabytes, frequently terabytes of space. There's a lot of trajectory data here. And so all of a sudden, this isn't just about implementing the weighted ensemble algorithm. It's implementing it in a way that can actually store the results and analyze them in a way that is efficient and, if possible, convenient. So what I'm showing here is a typical structure of a weighted ensemble simulation. So we start with two replicas. And after 5 iterations of the weighted ensemble algorithm, we wind up with 5 live trajectories. We've killed off 3 of them because, or recycled 1 of them, presumably because we're oversampling regions of space that we don't care about, or perhaps we've reached a target state and we need to start a new simulation over. And so people who have taken some computer science will recognize this data structure. This is a tree. And so the simulation that starts here leads to a number of other simulations. They share history, right? So the simulation that starts here, this trajectory shares history that started from here. This trajectory D down here shares history that started from here. Trajectory B has history that started here. So all of these trajectories have this little bit of dynamics in common. And so we wanted to take care to make sure that we only stored this data once. All right. Another primary concern was that we ought to be able to scale this method from our desktops that we're doing exploratory analysis on to the supercomputers that we strongly suspected we would need to run this on eventually. And so from the very beginning, we had this notion of, okay, how do we make sure this scales from the ground up? All right. And as I mentioned before, we wanted to be really sure that this software could grow with our understanding of weighted ensemble methods. So how best to do weighted ensemble sampling? You just heard from 3 people that this is evolving, even 6 years after the software was conceived. And so themes that will emerge are, we want to be able to do weighted ensemble sampling, we want to be able to change this code as we see fit, and we want to be able to store our data in a manner that lets us actually store it so we don't run out of space. All right, so as far as running this in multiple places, concretely we developed the software on Linux, and it runs on Linux, which is what's used at all XSeed sites, for instance. So WESTPA will run pretty much wherever you can get computer time. I'm sure there's a counterexample out there, but because we developed this software in Python, which is itself a highly portable language, the barrier to moving this code to a resource that we haven't run it on is substantially lower than it otherwise might be. You essentially only have to get Python running, and then WESTPA will run on top of it. So another advantage to using the Python programming language for implementing WESTPA is that we can rapidly test new algorithms. And we can do this without substantial decrease in efficiency. The scientific computing ecosystem that has grown up around Python is focused on efficiency, both in memory use and in speed. And so despite the fact that this is an interpreted and expressive programming language, we can run the really important stuff at C or Fortran speed. And importantly, WESTPA is based on standard scientific computing libraries that are being driven, whose development is getting driven by a pretty large cadre of industrial and academic researchers. And so we're really leveraging tools that already exist to make these simulations work, and to make them work anywhere, and to make them work quickly. Now, conveniently, all of the packages that WESTPA requires are distributed in the Anaconda Python distribution by a company called Continuum Analytics out of Austin. So the guy who originally developed the numeric extensions to the Python programming language went on to found a couple of startup companies. The first one, Mthought, is focusing more on the business world, and Continuum Analytics is focusing more on the academic world, as far as I can see from my academic perspective. But you can download this distribution for free. It's not a click installer because you're running out of command line, but it's a single command installer that gives you everything you need to run WESTPA. So we've written this software that hopefully runs effectively anywhere, and it does in fact scale from the desktop to the supercomputer. So this is actual simulation data from P53 MDM2 peptide protein binding on the Stampede supercomputer. And we get perfect scaling from 1 core on out to 4,096 cores. So this kind of follows from the nature of weighted ensemble as a method. As Dan said in his initial talk, we don't have to catch these trajectories as they cross interfaces between bins. We just have to stop every now and then and ask the question, have we made progress towards a desired result? And so that question of have we made progress actually is very low overhead, at least compared to the fact that we're running 100,000 atom dynamics simulations. So I'm sure at some point we will hit a scaling barrier of it just takes a long time to ask the question, how many of our simulation trajectories have gone towards our rare event of interest? But at least for the scales, the level of difficulty that we've been working at, we haven't hit that limit yet. And so I fully expect to see this line continue out past 10,000 cores for the kinds of systems that we are studying. For the simple reason that the dynamics we're running are expensive, the weighted ensemble algorithm itself is not expensive. So you download WESTPA, you download Anaconda, you get it running on your favorite supercomputer, and you just keep scaling until you run out of cores to run on. So the next thing that we had to ask ourselves was, okay, well, how are we going to actually set up these progress coordinates? How are we actually going to do our binning? And immediately, just brainstorming led us to several different possible conclusions. And so one of the major focuses of WESTPA is being able to specify the progress coordinates you want to define progress towards your rare event of interest, and then subdivide that in a way that makes sense. Right? So this is a figure from the paper that we just put out on the WESTPA software that shows several different ways that we can divide up coordinate space. This is a somewhat contrived example of some process that occurs on a ring. Okay. But you can think of, there's probably several different ways to divide this. And one of the most simple ways is to think, well, okay, let's put a bunch of bins in the x direction, let's put a bunch of bins in the y direction, and just see where all our trajectories wind up after a certain amount of time. So rectilinear grids of bins. This is probably what most people think of when they think about dividing up a progress coordinate into bins in some way that makes sense. But that's not the only way, and we've already seen a couple of other examples using, say, Voronoi tessellations. So WESTPA supports that out of the box as well. I'll show you an example where these are developed adaptively. Lillian mentioned that she, in her group, has used multiple regions where different progress coordinates are in play. WESTPA supports that out of the box as well. So what we've got here is a coarse grid of 9 different bins. And within those grids, we've overlaid 3x4 smaller grids. So we're trying to focus sampling at the north, south, west, and east quadrants of this circle for whatever reason. Maybe this is where our initial state that we have to escape out of that's hard, and here's a transition region that's kind of hard to surmount, and maybe here's our target state that's hard to get into. We're focusing our computing power here, 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 and here, and not focusing as much in these corners. We can do that out of the box with WESTPA as well. So nested sets of bins. And finally, I guarantee you that at some point, someone's going to think of, well, I've got this crazy progress coordinate, and I've got to bin it in this really interesting way, and nothing that you provide gives me a way to do that conveniently. Well, we also give you the option of, if you can write a Python function that maps some coordinate to an integer, then we can bin on it. All right? And so this is a contrived example. You could, if we wanted to say bin radially around this circle, okay, you could probably set this up with some rectilinear grid in angle space. But for the purpose of this exercise, we wrote this little custom function that says, okay, which little sector of the circle do I fall in? Give me an integer. That gives me a bin to fall into. And it did not take that much coding. So we try to give you convenience, flexibility, customizability, and then, if necessary, ultimate customizability to achieve your research goals. So we can run WESTPA just about anywhere people are doing serious scientific computing, or at least get it running quickly if we haven't run it there before. We can scale it from small to large scale. We can bin our progress coordinate effectively. So I still haven't talked about running this software with multiple dynamics engines. And in fact, that's been built in from the start as well. So here's the same picture again. So I want to walk you through a little bit of kind of the theory of how WESTPA looks at trajectory data. That's going to become important as you work through the hands-on examples later this afternoon. So we have all these different trajectories that start in two places, and we're going to run them for some discrete time interval tau. So that might be 50 picoseconds or 100 picoseconds. Every tau, we stop and ask each walker, each trajectory, have you made progress towards the rare event of interest? All right. And so at that point, we resample the trajectories, and we say that we've concluded one iteration of propagation and resampling. Okay. So what we do is we provide our dynamics engines with information about what's going on. So specifically, what iteration number are we on? Are we on the first round of propagation before resampling? Are we on the second round of propagation following the first resampling? Are we on the third round of propagation following the second resampling? We provide our dynamic software with what iteration of the algorithm we're on. And then we also assign every one of these little tau length segments of dynamics with an integer that identifies it. So a segment ID. And then we we pass user configurable paths or file names, as you prefer, to the dynamics engine that says, okay, where is a given dynamic segment starting, right? So this segment here, is it starting from the end of this trajectory or the end of this trajectory? So we pass that information along to the dynamics engine. And so between iteration number, segment ID, and these user configurable paths, we can tell the engine where we get our initial data, our initial starting point for a simulation, and where to put the output. Okay. And then typically the user will write a shell script to tell the dynamics engine where to find this information, where to put this information. So who here has heard of a shell script? Okay, most hands. Those of you who haven't, this is not magic. This is just what you would type at the terminal to get your simulation to run. Only we're going to put it in a file, and we're going to hand that file to WESTPA. And WESTPA is going to run that file once for every one of these segments. And it's going to send enough information to it by way of environment variables, which are just predefined variables inside the shell script, where to find information. So Adam's going to walk you through a lot of this in great detail this afternoon. So this is going to become more concrete as you go. So if you're feeling like, what the heck does all this mean? That's a lot of text, right? But this is mostly here for posterity. We're going to unpack this as the day progresses. All right, so to give you an idea of how well this is working, that's not a word, how well this has worked, we've done this with GROMACS, AMBER, NAMD, OpenMM in two different ways, both loose coupling, where we call an external program as if it were GROMACS, AMBER, and NAMD, and also tight coupling. So inside Python itself, to reduce whatever overhead we can of starting and stopping the dynamics. We've interfaced this, as Lillian has said, with the University of Iowa Brownian Dynamics code, and then as Rory's going to talk about, with spatial and non-spatial cellular models like BioNetGen and MCell. So because we've chosen a fairly generic way of getting information to the dynamics engine and back out, that's the secret to getting it to run anywhere. And pretty much all the end user has to do is to write a little shell script to make this interfacing happen. And we post some of these examples online, so you're not going to be alone in your efforts to get this to talk to your favorite dynamics code. Okay, so you can run simulations. You can run them with your progress coordinate of choice and binning of choice. You can run it with your dynamics engine of choice. Okay, so now you have 4 terabytes of data. You need to do something useful with it. We also provide a suite of analysis tools to help you do that. Okay, so I'm not going to read you this list. Again, this list is provided for posterity, but what I want to point out is that WESTPA ships with the tools that you need to get information back out of your simulations. So assigning probability distributions to observables. Asking questions of how would my kinetics and probability distributions for observables change if I changed the binning? So binning is a work in progress. You might not know off the bat what is the best way to divide your progress coordinate. Well, you can change that on the fly, and we give you the tools to ask what might be a better incarnation of these bins be. You can trace out individual trajectories for visualization or analysis. You can ask thermodynamics or kinetics questions. You can go and recalculate a new observable over an entire data set in a massively parallel fashion. So if you decide that you want to look at something completely different after your simulation is done, we provide a tool to let you go back to your supercomputer of choice and run a massively parallel analysis on this data. And we can also do things like ask questions of event duration distributions, the TB that Dan talked about earlier, to try to characterize path ensembles. So again, this table is here for posterity. It's not complete, but the point is we try to give you some tools to at least make some headway in running and analyzing these simulations. If those tools don't exhaustively complete the analysis possibilities that you want, because they won't, eventually, sooner than later, someone's going to ask a question that we haven't thought of. We take care to store all our data in a cross-platform file format called HDF5. If you've never heard about this before, you don't need to worry too much about it, other than data is structured in groups, just like a file system. And this data can be read with pretty much any tool you want. So what I'm showing you here is a third-party visualization tool that you can download from the HDF5 website. So HDF5 is developed at the University of Illinois. It's driven by lots of different fields, but I want to say that it originated due to a collaboration between the University of Illinois and NASA for storing massive amounts of information that come from, say, stellar probes. And so this has existed for a long time. It's very efficient in space and speed, and more to the point, you can access it from any programming language you want. You don't have the analysis tool that you want, you can write it in Python. You can write it in C or C++ or Fortran or MATLAB. You can, if you're a statistician or you're statistically minded, you can do it in R. There are HDF5 libraries for all of these. And so we store all of our simulation data and give you a map for it so that you can get at the data in the way that you care about. So it's not quite that you don't have to decode a file format. You have to know where to look to find, say, the progress coordinate data for the second iteration of your weighted ensemble sampling. But at least you don't have to write your own hand-coded binary file decoder to get at the data that you want. So this is part of trying to enable you to do research in a way that suits you rather than the way that suits us as the developers of this software. Okay. So that's the turbo introduction to the core features of WESTPA, the things that we've developed that we think will make it a useful package for you as scientific researchers. But the point of this talk is to act as a bridge between the methods talks of the morning and the hands-on tutorials of the afternoon. So you've probably been asking yourself through this morning, what does this mean for me? What do I need to know to run a weighted ensemble simulation with WESTPA? So, well, first of all, you need a progress coordinate. This has been alluded to several times. There's a fairly vigorous discussion in the literature of how do you select a good progress coordinate? What are some pitfalls or benefits of choosing a progress coordinate? How do you do it? That's a scientific question, and it's one that you need to kind of answer on paper before you even sit down to use the software. So let's assume that you at least have a guess for a progress coordinate. Weighted ensemble sampling, the correctness of weighted ensemble sampling doesn't depend on getting this right, but the efficiency does. The good news is that scientific intuition will at least get you in the ballpark to start exploring what you might want to explore with your rare events, and then you can come back and evaluate, have I made a reasonable choice? So if you have a progress coordinate, then you have to at least take a guess for how to partition the progress coordinate into bins. So weighted ensemble stops, assigns trajectories to bins that answer the question, how close am I to a binding event, or not a binding event, a rare event of interest? So you need to at least have a guess of how to divide your progress coordinate. And this can be adjusted as the simulation progresses. And this is actually pretty critical because you don't know a priori if your progress coordinate is decent, and you don't know if your binning is decent. And so we allow you to adjust this as the simulation progresses to make sure that you're always making progress towards the rare event of interest. Right. You need to pick a value for how often you're going to stop and ask this question, is a given trajectory making progress? So we usually call that tau. And a limitation in the current code base is this cannot be updated as the simulation progresses. I'll address that limitation in a minute. But this is not as big a problem as you might think initially, because it turns out that how finely you bin and how often you resample they're not quite two sides of the same coin, but it's pretty close. So in practice, this hasn't proven to be too great a problem for us. We simply adjust our bin boundaries rather than adjust our resampling frequency. We are addressing this in the code. We'll get to it. All right. So once you have all these kind of scientific questions answered, then you need to sit down and say, I need to be able to run a brute force segment of length tau. All right. So if you're going to wire up your favorite dynamics engine to WESTPA, you need to be able to run dynamics with it. And you need to be able to extract progress coordinate data. And so a good starting point for running a weighted ensemble simulation, after you've kind of answered these more scientific questions, is can you run 50 picoseconds of MD in Amber? And can you get the information that you've defined as your progress coordinate out of it? You can and should sit down and do that by hand before you try to wire this up to WESTPA. But if you can do that, then WESTPA is going to give you the tools to run several million little short segments of length tau in a coordinated manner. Okay. To do that, you need to have a little bit of experience in writing shell scripts. They often look intimidating, but it's not as bad as it could be. You'll see in Adam's presentation later today that this is not much different than if you were sitting and typing and running Amber at the command prompt, for example, if you're running an Amber molecular dynamics simulation. And then if you want to do some crazy stuff, if you want to go beyond the boundaries of what kind of we have anticipated most users will do, then you might need to know a little bit of Python coding to do customized progress coordinate calculations or something. But the point is you only need to know a little bit. And there are resources to help you get off the ground in this, both generically, how do you do scientific computing in Python, and specifically, how do you do it with WESTPA? Okay, so this is all summarized in this diagram. So there's a version of this that's in the paper we just published on WESTPA. So WESTPA kind of does the yellow and the blue for you. So WESTPA manages a weighted ensemble simulation with all its data storage and all its dynamics propagation. It'll handle farming out the propagation to a single core on your machine, or all the cores on your machine, or a bunch of cores on your favorite supercomputer. It'll handle the trajectory resampling that we've been talking about all morning, and it'll handle how do you store information that you need to do that resampling. But then it's going to be up to you to set up your dynamics engine to run, to calculate the progress coordinate, to store the data, and to divide the bins. But as you'll see this afternoon, we give you templates for how to set this up, and you don't need to do much more than you would already be doing to run brute force simulations. A little bit, but not much. All right. So I don't want to spend too much time on the nitty-gritty of this, because I've already been talking for a fair amount of time. You've been here for a fair amount of time this morning. But in practice, this is what this looks like for a GROMACS simulation. This is the sodium chloride association and explicit solvent example that's packaged with the WESTPA distribution. When you run this, you get a tree of files that looks something like this. And the weighted ensemble simulation itself is described in two different places, as you'll hear about later this afternoon, and as is documented in the distribution. General simulation parameters, things like what are my bins, How many time points do I have in a given tau worth of dynamics, that sort of thing. That's defined in a little Python file. If you don't know Python programming, don't worry about it. You just have to change a couple of lines in what we prepackaged for you. The reason that this is in Python instead of somewhere else is this was the best compromise between clarity and flexibility that we could find. This is how we would not get in your way trying to set up the bins that you want to set up. Things like, where do I store my data, is stored in this west.cfg file that you edit with your favorite text editor, and you'll hear more about this afternoon. Tau worth of dynamics is run, and then the progress coordinate is extracted by this little script that's packaged called runseg for run a trajectory segment. We'll go over that this afternoon as well, but WESTPA hands this script information of where do I find my starting point for a given dynamic trajectory, and where do I store my data as a result. And you get this nice little tree of, in the first iteration of weighted ensemble sampling, trajectory number 0, because this is computer science and people start counting at 0, at least in the C tradition. Trajectory 0 gets its initial point from some initial distribution that we've specified elsewhere, and then it writes out the native GROMACS output in this given directory. We get a configuration file, we get a trajectory file, and we get a log file that contains the energetics. All right, we get one of these directories for every tau worth of dynamics that we run. Now, in addition to that, we get critical information stored in this HDF5 file called west.h5. That contains information on what is the statistical weight of this walker. What's the statistical weight of this walker? What is its progress coordinates, so that we can ask the question, have we made any progress towards our rare event of interest? And so as you're thinking about setting this up for your simulations, you'll probably set up a structure something like this, either by taking our example and modifying it, or kind of like we did, just kind of working your way towards this is a logical way of organizing your data. Okay, so this is a lot of information, and we're approaching lunchtime, and I'm aware of this, but it's going to become less abstract as we go. Okay, so I want to note before I conclude that this is research. You have always something else you want to do that we haven't thought of as developers, and so we've tried to give you the tools to do that. So first of all, you can calculate the progress coordinate however you want. Typically, this will be done using the tools of your native dynamics engine. So if you're using Amber, you'll use CPP-Traj. If you're using GROMACS, you'll use the suite of GROMACS tools that they provide to do trajectory analysis. Or you can roll your own in Python. And that's typically what happens after on the third or fourth weighted ensemble simulation that we've run, is that we say, okay, let's forget about doing this with shell tools, let's do this with Python, because we have more flexibility that way. So that's supported out of the box. If you want to modify the simulation loop, as we'll hear about a little later, we can, there's a facility called plugins that let you write little snippets of Python code to modify the WESTPA simulation loop as it goes. And just to give you an idea, Josh Edelman and Michael Graves' group implemented a string method to toss a trajectory through the lowest free energy region. And to do this, he had to adaptively redefine the bins as the simulation went on. He did this in just a few hundred lines of code using the plugin facilities that are provided by WESTPA. The point is that you don't have to rewrite big chunks of WESTPA to do what you want to do. But if you want to rewrite a big chunk, you can. If you want to try out a completely new resampling procedure, well, WESTPA lets you completely replace this part of this diagram. So we call this modularity. And you can do this for a given simulation and tell it to load this modified module at runtime. So you don't have to hack on the pristine copy of the code if you want to change how WESTPA runs. Okay. So if you want to do more than we have thought of, we've tried to give you the tools to be able to do that effectively and efficiently. All right. So now what? Now we're going to hear more about how this might benefit you, how you might go ahead, how might you go about using this in your own research. So we'll hear more about that today, and then when you go forth from here, these slides will be posted online. And if you want to learn more about this software, you can consult the tutorials that are on the wiki and are distributed with WESTPA itself. All right, so this link is in the JCTC paper if you don't want to write this down now. This link is also going to be in these slides, which we'll post, unfortunately, to this very wiki. So maybe you want to write down this address, and then you can find the rest.
It's not on the website.
All right, so we've got packaged examples to show you how to do this for a suite of dynamics engines. All of this is housed on the wiki that Lillian very graciously hosts here at University of Pittsburgh. This includes documentation, a checklist for things that you might want to make sure you know before you run a weighted ensemble simulation, and some of the best practices of kind of how do you avoid the major pitfalls that we've found. They're not so major, but there's some subtleties just that can easily get lost as you're writing these little scripts that drive a few million rounds of little tau worth of dynamics. And so we've got a little checklist provided to help you sort out what you need to do and how you need to do it.
Which is good for even experts.
Yes. Yes, fighter pilots have their checklists, even if they've been flying their jets for 20 years. It's a very good point. All right. So because there's a lot of interfacing that has to be done, there's a little bit of shimming to get WESTPA to talk to Chromax and Amber and to get WESTPA to run on Stampede or your favorite cluster. We've got links to these scripts on the wiki. This also includes little useful analysis scripts that kind of build on the tools that I mentioned earlier. Okay. And then, perhaps most importantly, we've got this Google group set up. So you can ask questions of other people who use weighted ensemble in the context of WESTPA. And then if you come across a bug, which eventually you will, or you have a new feature that you want to request, which you probably will, you can submit concerns or feature requests at GitHub, and then the developers will look at it and say, oh, okay, this is not a bug, there's just this configuration item that we have to document better, or, oh yeah, that shouldn't be happening, let's fix that. So we ask that you submit those to the GitHub site where development is coordinated. All right, so got to wrap up here. By the time that a release comes later this year, we will have a non-Markovian analysis tool to handle the kinds of calculations that Ernesto has talked about, hopefully in a very efficient and flexible manner. That'll be in the distribution eventually. We'll improve our documentation. Another interesting tool that we're going to add is a utility to start a new weighted ensemble simulation from existing data. So you could use this to replicate simulations, to do multiple lightweight simulations based on some weighted ensemble simulation that you've used to generate a starting ensemble. This also helps us to get around this issue of the fact that at the moment we can't adjust the resampling interval tau or the frequency with which data is sampled within tau. It's a major problem in terms of data storage and analysis to change this on the fly. Very difficult to do, very error prone. And so it's the error prone part that concerns us more than difficult. So difficult things we don't have a problem doing. Things that would screw up the user without the user even knowing, those we're very cautious about deploying. And so our way of making sure that kind of users don't shoot themselves in the foot with playing around with adjusting tau is that you have to simply start a new simulation with an adjusted resampling interval. And this utility will help you do that. And then we're also reworking the task distribution framework for greater stability so that when you run this on your favorite supercomputer, it runs smoothly and robustly. All right. There are many people to thank for this. And so I'll go very briefly through this, but I think it's worth spending the time because this is the culmination. The reason you're here is that lots of people have been working on this for a long time. I might have been the first one to sit down and start hacking on this, but I'm by no means the only one. And I'm very much in debt to a number of people. So first and foremost, Professor Chong for advising me in my PhD and in developing this software. It was just a wonderful experience of enough space to make my own discoveries, enough guidance to make sure I was on the right path. I very much appreciate that. Thank you especially to Dan as well for keeping keeping me on track and how to think about these simulations. Professor Grave as well. Ernesto and his former colleague Steve have provided a lot of feedback about, okay, how do we really want to run these simulations? What do we need to think about? I live on the interface between chemistry and computer science and physics, and my idea of how to run a weighted ensemble simulation might not be Ernesto's, and so I'm very much in debt to them for giving feedback about how this software should look. Development has been very much a team effort. So Dr. Josh Edelman, who is not here but might be at the informal dinner later, has done a lot of development along with Adam Pratt. Joe Kaus, who is an undergraduate at Mullions Lab, wrote the first TCP implementation for the parallel task framework, and he's now got his PhD in working at Schrodinger. So there should be a doctor here, Kim Wong at the Center for Simulation and Modeling wrote the initial MPI implementation for running this on clusters. David, Dan, and Nick were undergraduates who also made contributions to the code. Kevin O'Connor devised the WESTPA logo, which is on your little espresso mugs. And then we've had funding from a couple of universities and from the NSF. So none of this would have been possible without all of these people. So thank you very much for that. And thank you for your attention.
So we have a bit of time for questions for all of the morning talks, including Matt's, at this time.
So bidding, right?
Yes. Yeah.
It's not trivial. I mean, for a given tau, if you pick the wrong bin, you're going to get stuck, right?
Yeah.
And it's not going to be 100 times faster because it's right. So what is your best practice for dealing with that? Just come in the next day, so you get stuck, adjust the bin size. Can you do dynamic bins? Can you just have small bins at the energy barrier? What's the best practice for making progress while not doing a lot of unnecessary simulation? Which small bins would do, right?
Yeah, exactly. So all three of those have been done.
I don't like the one where I come in the next day.
Yeah. In practice, especially for exploratory simulations, that's what winds up happening. It's not the most optimal, but it is one of the most bulletproof. That said, this is why, like you said, you don't want to do that, and that's why, for instance, this string method was developed, why we've prototyped dynamic binning schemes. And Dan,
what happens when you apply Bernoulli to a simple reaction coordinate, single distance?
I mean, so that would adjust the width of the bins.
Because Bernoulli is adaptive, right?
Right. So, so if you ran Bernoulli binning on a 1D coordinate, you would adjust the bin widths and
it doesn't change the number. It's just the width.
I would have to double check on that, but because of the way this, particularly the plugin interface is structured, it would not take much to adaptively define new bins, and then they would automatically be used from that point forward. The binning in WESTPA is, it's kind of an as-you-go basis. When the code stops, it asks, what are my bins now? And assigns to them. So the most common use case, at least so far that I'm aware of, is fixed bins manually adjusted. But the facilities are there for automating that, and I think someone just needs to sit down and make that happen in a more general sense than has already been done with the string method.
Well, and I guess
Someone
Alex
else
will
want to add
talk
to that?
Well, Alex will talk about another adaptive strategy and
WExplore.
But I mean, the bins are important enough that it's you're going to sink a lot of computing time into this that it's worth coming in a few days, and yet you really have to do some experimenting. There's no, at least at this point, we don't have a foolproof way because the bins are everything, right? If you don't get them right, don't bother. But if you get them right,
I'll just make the point that usually when you're doing a simulation, you'd want to just do a relatively long, straightforward simulation anyway, just to make sure that you've set up your system correctly, and then you can look at what bins would I be visiting if my bin size were a given size. So you can use an initial kind of exploratory, just straightforward simulation too.
Right, but if you're looking at an unbinding event, a long simulation, the thing bound.
So
the
there's
whole time.
something that you would be using to track the binding, so the distance between these two things, and you want to, say, bin that in 2 angstrom increments. So am I even getting to the first increment in my exploratory simulation? So maybe I should make my bin size smaller, so I would be. That's,
Wait, so Nick over here had a question.
This might be a dumb question, but so in each iteration, if you discover that, like, say, one trajectory has progressed,
Mhm.
and you want to resample that, so you split it into a couple different trajectories.
Mhm.
How are those trajectories going to be different? Do you kind of like reset velocities of atoms? Or?
That's a good question. It depends on your simulation algorithm, right? So if you're doing cell modeling and you're doing stochastic differential equations, well, they're stochastic. You've got random numbers coming in. But if you're doing dynamics, chances are you need a stochastic thermostat. So this method really only works if there's a random number somewhere in your simulation loop. So as long as you can introduce that, you can do that.
So the preference would be not to use a thermostat like Berenson, where you have to randomize the velocities, because that would introduce more perturbation in there. Yeah, so ideally something like a Langevin thermostat or stochastic rescaling, where the random seed is built into the thermostat. Justin?
I was going to comment that returning to the bins thing, sometimes it's can be helpful to kind of adjust the I found it helpful to like remove bins on the fly. Like for example, with some of the remote that I'm working with viral counts and simulations, and I've had to do things like periodically remove some of the bins in order to push the simulation further and not waste time covering regions of space that have already been covered. And I've kind of got a hack for doing that by automatically rewriting some of the configuration files.
Yeah.
But
So why not merge the bins to make large bins in uninteresting places and small bins?
that's kind of what I do.
That's what you mean, okay.
Yeah, that's in essence, so I think that's something that we'll probably want to put in the code. If there's like some systems, there's a coordinate that's like you can define a screamingly obvious one-dimensional coordinate, and then you may have orthogonal coordinates as well that you include. But if there's a way, if you're mostly interested in kind of the leading tail, and it's a very expensive system, you may want to kind of prune back some of the bins behind you. And as David said, you're really making it one large bin, so you're not introducing any bias, you're just reducing your investment there. And that's something, we've done that in a few ad hoc ways, and it's, in fact, in folding data that's unpublished, but we've used that to fold some small proteins, and now Justin's doing it for capsid assembly, so we didn't show any of that data. But yeah, that's definitely, I think that's something that we'll want to put in soon.
This is kind of keeping with the spirit of the code, which is nobody really knows the best way to do adaptive binning yet. There's absolutely a need, because otherwise, yeah, you're spending all your time twiddling code. Exactly, exactly. And by the time we've kind of sorted out all these different potential hacks, we'll have an idea of kind of what's the right way to do it without shooting yourself in the foot. And that's the point when we might say, okay, that's ready to go into the code.